we're moving to the next paper, which I don't know very well how to introduce because it's a co-authored paper by two people who at this very moment may be hating each other or just being good terms, because it's a PhD student and he's Dr. Fata, right? And so Enric Perez, you know him well from the University of Barcelona, and Blai Pie, well, also well known by some of you, but perhaps not so much. And he's a PhD student of Enric, and he's going to read his dissertation in September, is that? So he's a quasi-doctor, and you're going to present the whole thing on your own?
Well, okay. Can you hear me?
Yeah, does it work?
Yeah, it's a part. I mean, we couldn't put the whole thesis in this presentation. Can we take this? Okay. Let me move. Yeah. Okay. Well, as Jaume said, it's this is this presentation is the whole. Well, it's not the whole, but like the title is the same as my dissertation. And what we intend is to explain the experiment of Stern and Gerlach in its theoretical context, like to understand how was this experiment motivated in the framework of the old quantum theory, and how were its results read back then. So the title, this long title, could otherwise be put that way. What is the historical role of the Stern-Gerlach experiment? So just in case that some of you don't remember, I'll just revisit very briefly what's this experiment about. So the experiment starts in an oven, which is, we put some silver there and we heat it up, so we produce a beam of silver atoms, and then we collimate this beam through two slits, and this collimated beam passes through an inhomogeneous magnetic field, which is produced by an asymmetric magnet, this V shape of the magnet. And this inhomogeneous magnetic field is key to this experiment because it will exert a force on the magnetic moments of the atoms depending on their orientation. The force will depend on where are they pointing, the angle. So in the end, we collect these silver atoms on a screen, on a collecting plate. And what was key in this experiment was the difference between the classical and the quantum expectations. Classically, you expect a spread out region with deposited silver atoms with a maximum at the center. And the quantum prediction is that you would have a discrete set of beams. For example, in the case of silver, since there is only one valence electron with, nowadays we know, spin 1/2, but it was not known back then, you would expect only 2 spots on the screen. So this is the experiment. What we'll be talking about in this talk, this talk is divided into 3 blocks. First, we start with the theory. Before the experiment, we look for the motivations of the experiment, and the main motivation of this experiment was space quantization, which was the first quantum model that was able to explain or partially explain the Zeeman effect in a quantum theoretical framework. Then we'll move to explain some details of the experiment itself. We will not give a detailed account because there are some nice papers explaining. The most famous maybe is that there are 2 papers by Friedrich and Herschbach who give quite a great deal of details. We'll just add some things here that we believe are missing from these accounts, from the Stern-Gerlach experiment. And finally, we are going to get back to the theory and see how in 1922 theoreticians reacted to these results, and we will be surprised to see that there was not that big reaction. Well, let's start with space quantization. As I said, it was the first model within a quantum theoretical framework that could explain the Zeeman splitting. It was proposed by Sommerfeld in 1916, but before explaining this space quantization, I will very quickly revisit Sommerfeld's quantization. What Sommerfeld had done in the end, the last months of 1915, was to treat the electronic orbits as a 2-dimensional system in polar coordinates, and he could quantize these 2 polar coordinates, the radius and the angle. So with these conditions, he could get as we know, for different energies, different sets of ellipses or circumferences. And one first thing to keep in mind here is that Sommerfeld excluded the orbit with eccentricity 1, because it is a straight line that could go through the nucleus, so it was mechanically forbidden that it had to be an unstable orbit, and this will be important later, this exclusion. What Sommerfeld realized in 1916 was that if you add an external field, an external magnetic field, which defines a privileged direction, you can no longer treat it as a two-dimensional system. You need to move to a three-dimensional system in spherical coordinates. So for this treatment, for that figure, we need to consider that the field is along the vertical axis. So what before used to be the azimuthal variable, the azimuthal quantum number, now is divided into two numbers, one along the equator of the system defined by the external field, and another one which could be a latitudinal quantum number. And of course, these two latitudinal and equatorial quantum numbers add up to the azimuthal quantum number. Practically, what it means is that not all orientations are possible. Now only a limited set of tilts of this azimuthal plane are allowed. Like, it's exactly what happened with the ellipses before. We had a limited set of ellipses, now we have a limited set of tiltings. How many tiltings? Well, Sommerfeld discussed it. Usually he used this figure for quite a long time to illustrate how many angles you could have in this space quantization. So we'll not only explain Sommerfeld's prediction, but also Bohr's. So in 1916, in the first, sorry, I should have explained what's in this figure, actually. In this figure, we still have the magnetic field is in the vertical direction, and the black lines here, these straight lines, are projections of the orbit against the screen. So this could be an horizontal orbit, and this could be a vertical orbit, and so on. So in 1916, using this figure, he predicted that there could be 2n orientations for an nth quantum state, where n here is not the total quantum number, but only the azimuthal, so that the angular momentum, the total angular momentum. And in this paper, he didn't give much detail why it was 2n. He just explained how to produce this figure, and he said that we can see that there is 2 in this case, 1, 2, 3, 4 in this case, and so on. And we believe that he actually made a mistake, because 3 years later, in the first edition of the Atom Bomb, he predicted, using this same figure, that there could be 2n plus 1. And in that case, he really explained how he found this 2n plus 1. So the first thing that he said was that since there is to be a Larmor precession inside, so if we have, for example, for this oblique orbit here, if you put it inside the magnetic field, this orbit performs a precession. So actually, this orbit is the same as this one. So he could connect some of the orbits, so there should be less. But then he also argued that there is a left-handedness or right-handedness of the orbits. So for each of these orbits, you can have the electron turning right or left. So in the end, you just need to add up the numbers, and you find that there is 2n plus 1 possible orientations. 1 year before that, in his very important paper on the quantum theory of line spectra, Bohr had made his own, had adopted the space quantization of Sommerfeld. He made his own exposition of it, actually, and he subscribed this kind of interpretation by Sommerfeld, but using one of his very important principles, the adiabatic principle, Bohr could rule out one of the orientations that Sommerfeld had included, and this is the vertical orientation, the orientation which have no angular momentum around the axis defined by the external magnetic field. And he could do it, he could exclude this orbit by connecting this orbit with an adiabatic transformation, with a slow transformation, adding an electric magnetic field, and at the same time removing very slowly the magnetic field. I don't know if I said magnetic, I should have said electric and magnetic. So you add one of them and remove the other one. So in the end, he could connect these orbits with orbits that had been proven to be forbidden for the Stark effect because they collided with the nucleus. So the same exclusion that Sommerfeld had made for the eccentricity 1 orbits, Bohr could propose for this vertical orbit. In the second edition of the Atom Bow, Sommerfeld mentioned that Bohr had this prediction, but he didn't subscribe it. He just said in a footnote that Bohr argues that with an arbitrary transformation, this should not be allowed. In 1922, though, in the third edition of the Atom Bow, Sommerfeld made a deeper revision of the book. Like here it's important that the first and the second editions are very similar, only few corrections are made, but the third edition is renewed, is much more extended, and Sommerfeld actually included many things from Bohr's theory, like the correspondence principle and the adiabatic principle. So he himself could develop the reasoning behind this exclusion. So in the end, Sommerfeld in 1922 subscribed Bohr's predictions. So, well, about space quantization, we have said that it was proposed to solve the Zeeman effect, but how did physicists regard this space quantization? Well, the first success, we could argue that the first success of space quantization was the explanation of the Zeeman effect, but it was only a partial success because Sommerfeld, with these models, could only explain the normal Zeeman effect, so the triplets of the Zeeman effect, but he could not explain the anomalous Zeeman effect. So this could be the first success in 1916, and this is why actually Bohr included it in his theory. A negative point of reception could be, I mean, this is something that is said afterwards, a posteriori, that it seems that there was some kind of rejection, some kind of skepticism against space quantization, because many physicists regarded it as just a purely mathematical tool. They doubted that actually the orbits could be aligning themselves with the magnetic field. And well, we will see that this could be one of the motivations to do this Stern-Gerlach experiment. Then another positive, and this is a very personal reading of mine, but I believe it's a positive reception of the space quantization, is the introduction of the inner quantum number by Sommerfeld himself, because the inner quantum number is nothing else than an inner space quantization. Instead of putting an external magnetic field, we have the inner shells of the electrons which produce a magnetic field, and this magnetic field interacts with the outer electron, giving some energy splittings and some selection rules and so on. Although, as I said, this is again a partial success because the inner quantum number had a limited success. And finally, maybe the strongest point against the space quantization is the issue of the birefringence. The birefringence is when we have a gas. If we apply a magnetic field to it, we expect, or classically, we would expect to have different refraction index in different directions of polarization of light. And it was actually well known at that time. It had been measured, but from the classical point of view. If you took classical models and added the limitation of a space quantization, what you expected was a kind of quantum birefringence, which was a much stronger birefringence, and that had not been observed. And this last one is one of the main points that Stern uses to motivate his experiment. He says, there should be this strong birefringence, we don't observe it, so let's go and observe directly the space quantization with an experiment. So let's move now to these experimental details of Stern and Gerlach. As I said, I will not explain in a lot of detail what they did, how the developments of the experiment were made. The first thing that we wanted to emphasize of this experimental setup is that the Stern-Gerlach is not an isolated experiment. The Stern-Gerlach is part of a much wider project, which could be called the molecular beams experiments. And these kind of experiments were performed for the first time, were invented, one could say, by Louis de Noyer in Paris in 1911. What he did was he placed in a vacuum tube, in a vacuum cavity, he placed a sample of sodium and 2 slits, 2 walls to make 3 cavities. So he would heat up this sodium, and then the gas of sodium, the evaporated sodium, would fill this first cavity. It could go through the pinhole to a second cavity, and then yet to a third cavity. What Dunoyer observed was that on the walls of this cavity and this cavity, there could be deposits of sodium, but on the third cavity, only a small region here would have sodium deposited. And he interpreted this result as a confirmation of the corpuscular constitution of matter. One could say, I've made this picture, one could say that that's what he interpreted was happening with the atoms. Only an atom traveling in a straight line between these 2 pinholes could reach the third cavity. It's important to think that he believed that it was something related to kinetical theory for him. It was 1911, we could say that kinetic theory was already accepted, but for him it was still a further proof of this theory. And he actually proposed to call these methods. He saw that it was a very powerful method, that many things could be studied with this, and he proposed to use this name, Kinetic Experimental, which I have not seen in any other place. Nowadays we call it atomic or molecular beams. He would do few more experiments during the 1912 and 1913. Also Robert Good, who appeared in the previous presentation, would do some experiments. And I have also found one paper, I think, by Irving Langmuir and by Knudsen. I think it's Martin Knudsen. Well, I'm not sure. So there is a few physicists working on that method. It was regarded as a powerful method, but still, it was not very used during the 1910s. The first one to really exploit all the power of the molecular beams would be Otto Stern. He arrived in Frankfurt am Main by the beginning of 1919, just right after the end of the First World War. And the first experiment that he proposed was this one. I will not explain it in much detail. Just with this experiment, what he tried to do was to measure the mean velocity of the Boltzmann distribution in a gas. So this is a void cavity, no, vacuum cavity, sorry. So, and the whole thing can rotate around this axis. And actually, if we look at this experiment from above, what he did was in the middle, he had a filament and he produced a beam of silver atoms. They could pass through 2 slits, and due to the rotation of the whole experiment, he could measure the displacement of this beam, and in this way he could determine which was the mean velocity of this beam. So again, the first experiment of Stern regarding molecular beams was an assessment of kinetic theory. And it was quite a success, this experiment. People were quite impressed. And in Frankfurt am Main, it was kind of famous. And even Born, Max Born, who was a theoretician, got involved in an experiment about molecular beams. He tried to measure the mean free path of silver atoms in different pressures, but he could not manage. His experiment was a failure, at least in 1920 and 21. So he would ask Stern for some help, but Stern denied him this help. He decided to stick to his own schedule. And of course, as you can guess, the next item in his schedule was the verification of space quantization. So let's now give a brief experimental timeline of the experiment of Stern and Gerlach. We believe that Stern started working with it early 1921. We don't know the exact moment, but it has to be something around that time. But he published the first paper in August 1921. It was like a programmatic paper. He described the whole experimental setup, the objectives, and he gave classical and quantum predictions. So it was very a programmatic paper. By that time, a few weeks or months before this, Gerlach would join the project, and actually Stern would leave to University of Rostock. So from September 1921, Gerlach was alone in Frankfurt developing Stern's experiment. And it was quite a challenging experiment, and they got the first success by November 1921. and they could observe for the first time a widening of the beam. So they could see that the beam turning on the magnetic field could be elongated, it would be longer on the distance of the direction of the magnetic field, but still there was not enough resolution to see if it was to distinguish between classical and quantum predictions. Then they went on, it's reported that Stern went to Frankfurt during Christmas vacation to try to work with the experiment, and after Christmas it was a failure, they could not achieve the results, so they decided to give up. They couldn't. The key point here is that the technical difficulties were great, the alignment was very difficult, they had to keep a vacuum of 10 to the minus 4 millimeters of mercury during 8 hours with an oven at many degrees Celsius in there, so it was technically very difficult. They decided to give up, but early February 1922, Gerlach decided to give it a last attempt, and this last attempt was the first one that he actually could see the splitting of the beam. It was 8th of February of 1922, and we have this witness of Wilhelm Schutz, who was Gerlach's assistant at that time, and he was told to send a Stern telegram telling him Bohr had doch recht, so Bohr was right in the end. And the reason of this sentence is double fold, is that first they confirmed the space quantization, they saw a discrete separation of the beam, but also they saw 2 beams and not 3, because remember that Sommerfeld changed only in early 1922, so they still didn't know, there was still a difference between Bohr and Sommerfeld. And well, just to finish this timeline, they published the results around April 1922, when they had performed some more accurate measurements. And this picture, I guess you have all seen it lots of times. This is a postcard that they sent to Bohr a few days after this measurement. And this is the original measurement, supposedly, which we see here the beam projected. It was a rectangular slit, so it's the beam without field. And with field, there is this 2-fold separation of the beam. So, how was the reception to these results? This postcard that they sent to Bohr was not the only postcard sent. They sent many of those and many letters informing colleagues around all Europe about their findings. And there was a huge response to that. People were happy about the Stern-Gerlach. There is lots of, well, not lots, but many letters, congratulations, or people asking for further details. But this just goes on for a few weeks or a few months. After, say, half a year, there is not much talking about the Stern-Gerlach anymore, or at least not very much critical talking about this topic. And we could only find one paper discussing this issue from a theoretical point of view. And it is a paper by Einstein and Ehrenfest. They sent it to publication by the end of August 1922, so 5 months after the findings of Stern and Gerlach. And in this paper, what they do is they try to understand what's going on inside the experiment of Stern-Gerlach from a quantum theoretical point of view. Because it seems that the Stern-Gerlach confirmed Bohr's theory, or even Sommerfeld's space quantization, but they wanted to understand the whole picture. And the thing that worried them was how did the atoms get oriented inside the magnetic field. So if you're sending atoms, silver atoms inside a magnet, these atoms originally are free of any magnetic field, so they can point wherever they want. And when they suddenly enter the region of magnetic field, what we know is that they perform this Larmor precession. And if in the end there is only atoms pointing upwards or downwards, this Larmor precession, this cone needs to shrink, needs to end up only pointing upwards or downwards. So what they did is calculate, they did actually a semi-classical approximation, so a classical calculation with quantum corrections, we would say, and they computed that the time needed for this orientation to take place was about 300 years, which of course is a bit larger than the 10 to the minus seconds that the atoms spend inside of the magnetic field. So there was a problem, because the Stern-Gerlach, which was to confirm some quantum features, actually could not be explained, could not be understood from the quantum theoretical point of view. And they made two suggestions. To try to solve this, they thought, actually they discussed for quite a few months about this issue, and finally they got two proposals, two hypotheses. In the end, the hypotheses were even worse than the original problem. So this is the paper finishes that way. The first hypothesis is that the magnetic moments are always aligned with a certain magnetic field. For example, before, when they are between the oven and the magnet, they are aligned along the Earth residual magnetic field, and they are quantized. They are space quantized with any small magnetic field. The problem is that when they enter the Stern-Gerlach, they need to suddenly change direction, and they are not allowed to do any change of energy. So this needs to be an adiabatic process, but if it's a quick orientation, it goes against the adiabatic rules, like the adiabatic range of applicability. So in the end, this called for a violation of the adiabatic principle, which was one of the fundamental cornerstones of Bohr's theory. We just saw a few slides before how it was useful to actually assess that there were 2n instead of 2n plus 1 orientations. The second proposal they made was that after a collision, or when they suddenly entered this field, the magnetic moments would be, for a very short time, in a non-quantum state. And the transitions from these non-quantum states to quantum states would be very fast, so that could explain why it takes 10 to the minus 4 seconds instead of 10 to the 9. But they argued that this kind of transition needed to exchange radiation. So in the end, only charged systems could attain quantization. And this was it was disastrous because the neutral systems had been well known for a long time. They quote the diamond and the molecular hydrogen. So it was not acceptable for them to apply quantization only to charged systems. This paper, which seems to claim that there is a big problem, at the same time, we said that the Stern-Gerlach didn't receive much attention, so this same paper didn't receive much attention itself. It had 3 or 4 answers during 1922 and 3. One of these answers was Bohr, which in the paper of early 1923, he answered this paper by Einstein and Ehrenfest in a small footnote. He just disregarded all these arguments, and he tried to convince that there was no problem. There was also a paper by Born and Heisenberg in which they made other, could say, wild proposals to solve this issue, and some discussions, a couple of papers, I think, by Adolf Schmeckel. But in the end, one would say that after August or September 1923, we couldn't find nobody else seriously mentioning this problem, seriously discussing, seriously trying to find the solution. And we couldn't find the reason, of course, since we didn't have the documentation, why didn't they discuss? But we believe that maybe it's because the focus was moved to other issues, other problems. Usually it's used the word crisis of the old quantum theory, which 1923, 1924, it makes kind of sense, but we don't know for sure what happened exactly or why. Sorry, I don't know if I forgot something. Yeah. Well, yeah, no, that's all. So I'll just summarize. I don't know how am I in time, Jaume? Okay. I'll just summarize like the take-home message from this talk. We asked at the beginning, the alternative title of this presentation would be, what is the historical role of the Stern-Gerlach? So let's try to answer this very shortly. So first, we have seen that the Stern-Gerlach was supposed, and actually was, a confirmation of a space quantization. We have seen that there were some theoretical reasons to believe this is a space quantization, but yet it was a good assessment to observe it experimentally. Of course, I'm thinking all this in the old quantum theory framework, and not in nowadays way of looking at it. Second, we have also seen that Stern and Gerlach believed that they had confirmed Bohr's predictions as opposed to Sommerfeld, although this is the value of the experiment in that sense is much more marginal because we have seen that Sommerfeld, a few weeks or months before the Stern-Gerlach outcome, had already decided to, had already accepted Bohr's reasoning or line of thought. Third, we have put the Stern-Gerlach experiment in context, and it's actually nice to see that it all started with experiments related to kinetic theory, and this, actually the name molecular beams comes from the fact that this experimental method was really developed a lot during the 1920s and 30s, and in the end it was very useful for chemical measurements, for measuring properties of chemical molecules one by one. So this is a whole, it's a huge project, and the Stern-Gerlach is just one experiment, very famous for physicists, but there is much more to it than that. And fourth, we have just pointed, we couldn't fully explain, but we have seen that there was a poor reception of the results of Stern-Gerlach, and this, despite nowadays, the Stern-Gerlach is one of the most famous, or one of the famous, let's say, experiments in modern physics. And we believe that we want to emphasize this poor reception at the moment as opposed to the treatment that the priority is usually given to, or the high esteem all physicists have for the Stern-Gerlach. And there might be many reasons for this posteriori acquired importance, but we believe the main might be the spin, because the Stern-Gerlach is very useful to illustrate this elusive concept of spin. It's used in textbooks, it's used in classrooms every year to try to explain what is spin, and it is very illustrative experiment. So maybe this confuses a bit about what was the original role, because what we have seen is that clearly Stern and Gerlach had something very different in mind, and the way of reading results was also something very different. And that's all we wanted to tell you. Thank you.
Thank you. Oops. Okay, we've got 10 minutes or so. Let's start with Gyula. Yeah.
Thank you. I'm interested in the experimental tradition. Could we trace it even back to Hertz's experiments on cathode rays? Because the idea is that you have a beam of whatever, and then you apply some kind of diversion to the beam. And this looks like a similar concept. So
yes.
If you can elaborate on that, why do you think it's actually the origin in kinetic theory and not in the cathode ray kind of tradition of experiment?
I think the key point is that in molecular beams, in all these kind of experiments, we're dealing with neutral particles which are thermally accelerated. It's not that you have an electric field accelerating, so it's just thermal origin, and they can be at least, they don't need to be, because in 1920, I don't know the exact date, but around 1930, it was a huge success of Stern's team in Hamburg, that they measured the magnetic moment of the proton, so they don't need to be obligatory like neutral particles. But the key point of molecular beams is this, that you can work with neutral particles.
Alex.
Hey, thank you. I wanted to ask if you've done any research also on then the resurgence of interest in the experiment. When did that start? I mean, basically, who dug up the Stern-Gerlach and brought it to its central role it has in physics now?
It was a very interesting question that I believed that I could be able to do this during my thesis, but the thesis just kept growing. So I have left this for my first postdoc, let's say.
We'll get there. Martin.
Okay. First of all, thank you for having introduced space quantization in this clear way. I have a lot less trouble for tomorrow. One thing to the poor reception. My impression is that propagation experiments like the Frank-Hertz, like the Ramsau effect, like the Stern-Gerlach, play a very small role in the old quantum theory because it's essentially a theory about spectral evidence. And that's the main reason I see it, that it can only be something which confirms a concept, but not enrich it. I mean, which question would the Stern-Gerlach pose to this kind of theory working on the structure of spectra? One second thing about Bohr versus Sommerfeld. Do you know how the situation then turns out in the 1924 edition of Sommerfeld's Atombau und Spektralen? Because I believe the 2n+1 resurfaces in this. At least it does for the inner quantum number, for the statistical weights.
Yes, actually, for the inner, it's I think already in the 22 edition, there is already, yes, there is already, yeah, well, that's what I was about to, there is like, it's strange because Sommerfeld uses this 2n prediction for the space quantization, but then in another chapter of the book, in about inner quantum number, he mentions in a footnote that he's forced to accept 2n+1 possible states or orientation for the inner quantum number. And in 1924, not much changes. He just includes a section in the chapter explaining the Stern-Gerlach and the whole thing, but like there is not a huge change. I haven't looked at the inner quantum number, but of course Stern-Gerlach confirmed the 2n prediction from his point of view.
It should, because he talks about the Stern-Gerlach in the multiple structure chapter.
Okay.
There goes to 2j+1.
Okay. Well, we can show because I haven't looked at it in that detail.
Yeah, I think Shaul was next.
Thank you. I have also questions about the reception. First, you talked about the theoretical reception. Have you looked about experimental reception? So the sense of how much the idea was recapitulated by other experiments in different variations, which is also kind of reception. And second, I think that the concept of poor reception is only poor if we compare it to how famous the experiment is today.
Mm-hmm.
It was not poor from the evidence you put.
Yeah, well, I agree in the second remark because maybe it's a personal how do you say, distortion of it, because I was expecting this poor reception, and also this poor reception is not only about the experiment but especially also about this paper by Einstein and Ehrenfest. But I kind of agree that it's this poor reception already. Like, I'm doing history in all these 3 points. This 4 is in between, and this 5th I'm talking about nowadays. So of course it's a poor reception comparing what you would expect for such a famous experiment as Stern-Gerlach. And your first question was about the experimental reaction to it.
Yeah.
I don't know how many more groups started doing molecular beams in the 1920s. But what I know for sure is that Gerlach kept working with it a few years, and Stern really developed a huge laboratory in Hamburg, and he worked with I think Rabi was in. I'm not sure if Rabi is from later when he moved to the States, but for sure Rabi is one of the heirs to Stern way of working, and there is also the measurement of the magnetic moment of the proton. So he really developed a lot these methods, he himself. But I'm not sure about other developed beings during the 1920s.
Yeah, Christoph, I think.
Did I answer your first question, Martin? Did I? You're Martin, because I'm not sure.
We can talk about
Okay.
Yeah.
About the importance.
Yeah, it's on.
About the importance later. I mean, my hunch is that it's not so much a matter of spin, right? I mean, it probably would be still all over the textbooks if they had 3 dots on the screen, but about the concept of quantum mechanical measurement, right? I mean, that's why it so dramatically illustrates the non-classicality of measurement in quantum mechanics. And you know, the Einstein-Ehrenfest paper is the first work to point out how non-classical, how against classical expectations that fact is. So, you know, nowadays after, 70 years of debating the measurement problem, that is, of course, one reason why that has become so prominent. But it seems to me, at the time, right, the fact that you had these not classically explainable transitions didn't seem that different from having other quantum jumps, right? From having the quantum jump that emitted radiation in an atom, right? So there also an electron supposedly was changing its orbit suddenly, non-classically, and very fast, and there was no good explanation for that. So of course nowadays we can also see that as an effect of the effect of the measurement, a kind of measurement problem. But it seems to me that in the 20s, right, this idea that something happened that couldn't be explained classically sounded familiar, like a typical quantum thing. And so Einstein and Ehrenfest's worry probably seemed rather nitpicking, right? I mean, it seemed at the time probably that it wasn't that different from all the other quantum effects.
Well, actually, Bohr's answer to this paper is that, Bohr's answer to this paper is he suggests, in a rather complicated word, I would say, in a rather complicated phrasing, that he suggests to assimilate this transition inside the Stern-Gerlach to the transition between quantum states. But he then, I mean, this is what's on paper, this is what he published, but just a month after this paper got published, in discussions with Ehrenfest by letter, he acknowledged that he was not sure about his own solution because there were some problems about how could the energy be preserved and so on. So, but in the end, yes, this is the nowadays way of looking at it would be that. And I agree on the first remark that you made that this is not only because of spin. As I said, there might be multiple reasons for this a posteriori importance. I put here spin, of course, I totally accept that the collapse of the wave function is another important.
I just want to point out, though, that there's nowhere in the paper of Einstein and Ehrenfest is there any attempt to transfer the point of the transition to the impact of the screen.
No, I mean, of course.
That's way later where problems of measurement theory enter.
Well, but
some modern point of view, which would be very wrong to inject. If you read the
but that has
Einstein,
nothing to do with the measurement
Einstein
problem, right?
Ehrenfest has nothing to do with the measurement problem. The way they discuss the problem, you're just trying to understand what is actually the process during the transit of waves over atom through the apparatus.
But that is the measurement problem, that we don't have physical explanation of the transition.
There's nothing in the paper which suggests that something funny happens at the screen.
Well, that doesn't have to be. Why does it have to be at the screen? Something funny is happening.
Well,
That's the point of the measurement problem. Whether it happens at the screen
No,
or
well,
something
it does
at the
happen
board,
at the
that's what we're still debating
It
about.
does happen at the screen.
No, it doesn't.
Okay, something happens. Something happens behind Aaron. Aaron.
Thank you. I'm on a similar track to the previous questions about the reception. You said that it seems like the experiment was quite programmatic, that theory presented a problem, experiment set out to solve that problem, they did solve the problem, and then not very many people cared. And then it wasn't just time that passed, or maybe textbooks, pedagogy was your suggestion, but actually a new quantum theory, or a significantly different, anyway, quantum theory arose. And so I was wondering, the first sort of just basic question is, do you know who was the first or most influential beginning person to take the new, Heisenberg, Bohr, or Schrödinger, or Dirac perspective and look back at this experiment? And then the historiographic question would be, what does this tell us about the interaction of theory and experiment? And programmatic problem solving is maybe happens, but is not taken to be so interesting. And can theory perhaps go back and rediscover an experiment, or and if you have thoughts on this theory-experiment relationship for your story.
Well, regarding the first question, I will be ashamed not to be able to give you the three names, because we were discussing this on the train trip here, about that I should check these three names in case this question came up. I can only say that the concept of spin came in 1925, and it was not until 1927 that for the first time they realized that there was a problem with the Stern-Gerlach that needed to be corrected with the spin. So in a sense, I can tell you later. I have my thesis here. I just need to look the page. I cannot remember. I really cannot. And the second question was about the relationship between theory and experiment. Okay, this is something complicated. I'm not an expert on that, although I try to discuss it briefly in my thesis. The way I interpret it, like the reading I do of the whole story, is that, of course, there is a motivation, a theoretical motivation for the experiment. So, I mean, in the thesis, I'm talking maybe a bit naively about this concept of crucial experiment. You have theoretical motivation, then you do experiment, and it confirms one of the two. So, in a sense, this works in one direction, but it completely, in this instance, it completely fails in the other direction. This is the reading I have made. I haven't, as I said before, I haven't gone into looking how was the experiment reinterpreted in modern terms. But I think it's a really interesting question.
Okay, Blai, you won't deny this is a very friendly rehearsal for your Viva, for your defense in September. Okay, thank you very much, Blai. And as promised, we deserve coffee, which is down the corridor to the right, and we reconvene here at 12:30, that in 25 minutes, right?